So, hi to everybody. I am Martino Migliavacca, and with Andrea, I will talk about uROSnode, that is a tiny implementation of a ROS client running on microcontrollers. To give some background, we both work at the Artificial Intelligence and Robotics Lab at Politecnico di Milano. In the lab, during the years, we have the opportunity to build many robots, principally mobile robots from small platforms up to bigger unmanned vehicles. Building these robots, as you may know, it's difficult because every time you have to reinvent something from scratch to control your custom platform. So this is why we introduced R2P, the rapid robot prototyping. I presented yesterday during the lightning talk an overview of it. And it basically is something with a framework with a set of basic modules that implements the most common robot functionalities we need to prototype a robot. And the boards are interfaced with a real-time CAN bus protocol and with a lightweight publish-subscribe middleware. The goal of R2P is to implement and control the low-level software and of the platform. But then, of course, we have to implement also the high-level software, which is often developed with ROS. We are happy ROS users, but the problem we always feel with ROS is when you have to interface with the hardware. As many devices use custom protocols on a serial connection or USB connection or even Ethernet connection, but still with custom protocols. So usually you have a software node for each device that is directly connected to the device, and then the software node publishes messages, ROS messages over the ROS network. This is not, I feel, in the not what the distributed architecture of ROS is fostering. So, what we would like to have is many hardware devices that natively speak ROS language. So, for example, the SIC laser which has a Ethernet connection could directly publish ROS messages over the ROS network. Or we can have robotic platforms which subscribe directly ROS topics, and you can control the hardware and interface with the hardware as it was a simple ROS node. Another advantage is that hardware devices can then directly speak each other without the need of the connection to the computer, so you can reduce latency, and it's much easier to integrate new devices to your system. This is why we started developing uROSnode, which is a lightweight ROS client. It is not a port of ROS to embedded system. It is not a standard ROS client. It is just a library which can interface directly with ROS on microcontrollers. The target platform are modern microcontrollers like the Cortex-M family. And we decided to develop it in NCC, so it's easier to port to new platforms. And up to now, it already supports the main ROS features, like the XML RPC management protocol. It speaks the TCP/ROS data protocol, and it features the ROS topics, ROS services, and ROS parameters. Now I want to give Andrea the opportunity to talk about the implementation and describe how you can use uROSnode in your projects.
Okay, everybody. Okay. uROSnode is written as a modular framework, communication framework. We try to apply an object-oriented style on top of NCC so that it is easier to maintain, I think. We focused very hard on multi-threading so that we can use an operating system generic like POSIX or a real-time operating system like CBOS, and which is often used in embedded system. Real-time is also a hot topic, I see, at the RosCon 2013. We added a lightweight abstraction layer to interface to low-level drivers for communication, memory management, and multi-threading as well. The integration with the user firmware is assisted by the use of a code generator tool, and also the user is typically required only to write the function, the handlers for the topics and services, while the messages are automatically generated. By the way, I have a few notes about the XML RPC implementation, because there are some libraries outside which can be used in C, but they have wild memory management. They buffer everything and then do the parsing, then parse the contents. So that we developed a custom library to parse XML RPC messages and also stream them, which parses them on the fly, a single pass, so that we use the least possible memory we could on a microcontroller. And also the implementation was written to be easy to maintain by hand. So it is not the generator like with tools like Bison or Yak or so on. There are also some limits because we use a microcontroller, so strings and messages have a limit in size. And also we haven't added the compressed streams like a zip, which is sometimes rarely used by ROS core. So about the generation flow, we take the point of view of the user, so of the developer of the firmware. The user uses the code generator tool, providing a configuration file in which he writes the list of topics, topic services, and their types, and also other options. Then the code generator takes the descriptions of the messages and services from the existing installation of ROS on the development machine and generates the code for message types, their message marshalling and marshalling functions, and the stubs for the topic handlers and the services handler functions. Okay, this is an example of a configuration file where we write, for example, the node name, the topics, and as well. This is the configuration file to build a TurtleSim clone. So everybody, I think, knows the TurtleSim. And it's good, not only because of this, but also because it covers almost, if not all of the features needed to build a single ROS node. So it was a good benchmark, we'll see later. We can see the list of topics, so the names and the types with the classic ROS notation. Okay, this is an example of output code. Don't be scared. I know this is a syntax quite different from what you are used to see. So first, because it's C, so there is no namespacing and so on. But also because this is code automatically generated, but the user is only required typically to fill in the variables, the message variables, or read from them, like you always do also in ROS. And, but they can also be used to do optimized streaming and reading of messages on the fly as well. So I think it's a little more powerful than direct buffering of messages. Okay, to do some evaluations, we are using the gateway module provided for the R2P environment. This platform mounts modern microcontrollers from ST, which mounts an ARM Cortex-M core, which is very recent, the M4. It has 1 megabyte of flash memory, which is plenty of space because on modern microcontrollers. Also 192 kilobytes of RAM. It mounts a fast Ethernet port, which is used to interface to the ROS network. And as operating system, we chose CBOS real-time because it's very easy to build a new application based on it for a new firmware, and the WIP network stack for the management of the TCP/IP streams. So we wrote a TurtleSim clone firmware which was compiled with ZCC at different levels of optimization. This was done to see how big it was on the program memory and on the RAM. So we have some numbers here. In the best case, we found that the microROSnode requires less than 40 kilobytes of program memory. And on the memory, on the RAM side, we have proved that topics and services, which are handled by isolated threads, require less than 1 kilobyte each, which means that we can allocate even tens of communication channels at a time, even on such platform. Okay, we also made some communication performance benchmark, which are simple, but I think very significant, because we streamed one topic by varying the message size and measured the CPU usage. Here you can see on the left the transmission performance, on the right the reception. We have reached on transmission a throughput of 20,000 messages per second. This is limited when the message is smaller than 100 bytes by the ROS topic hertz on my host machine, which wasn't very fast. So the platform, the embedded platform, was even faster than my computer in doing this. And we also see that LUWP, which is the red, okay, the red line, has the biggest impact on the CPU. So it's not the fault of a microROSnode, the decrease of throughput when increasing the message size, but because of the TCP/IP processing. Likewise, on the other end, when we do the reception, we can see that we can reach around 10,000 messages per second. Here, the limit was also my host machine when messages were smaller than 1 kilobyte. And when messages were bigger than 2 kilobytes, we also reached the Ethernet saturation. So the performance when streaming and receiving streams is not impacted by microROSnode, but by the host machine, the TCP protocol, and also by the processing itself made on such a microcontroller. Okay, as a use case, we consider the omnidirectional robot, Tracker2, we developed in our lab. It is made out of R2P modules, hardware modules, which work in real time over a canvas. And as you can see, the gateway module we used for the benchmarks is used to interface to the ROS network. It also does some computation like kinematics, not only message production and consumer. The robot also mounts another computer which is only used as a ROS master and to stream data from a camera to a remote computer. So it is not used in this case for ROS processing. Okay, this is the schematic of topics between the R2P modules and the ROS nodes. As you can see, in the middle there is our gateway, which translates messages from R2P and the ROS and vice versa. The user controls the robot by sending the velocity set points and can read the distance of the obstacle near it, and can also display what is in front of the robot itself. This is a video recorded with 3 cameras. Okay, one on the left shows the robot. Below there are my hands, which control the tracker in a first-person view video game-like manner. And on the top right view, there is the application we wrote on the remote computer, which displays what's in front of the robot and the set points of which I made with my hands. Okay, we can see that the robot is very reactive, so microROSnode can process things very fast. We had no particular jitter on communication. On the camera, yes. So, you know, it wasn't a very good camera. Okay. uROSnode is available on GitHub. It's an open source project. It's already working. There are some demos on the GitHub repository. We provided the code with Oxygen documentation, so it's, I think, very well documented. Everything is documented. It supports the main ROS features. It's a very young project, so we have something to do, still to do, like the addition of the UDP ROS protocol for efficient communications, and maybe C++ wrappers to provide an API much closer to the current API of ROS C++. So it must be even easier to write a firmware like you do with ROS C++ on a generic computer. We are also very open to suggestions for future works, and we know that there are other projects doing similar things. When I started developing with Martino this package, there weren't many things on the ROS wiki, so we tried to start from scratch, but we are very open to new suggestions, and maybe, I don't know, merge with some project or work as a reference for something you have to do, something you don't have to do, like we did. Okay. Thanks for listening, and if you have questions, yes. Okay.
So you can use